Radioactivity. In 1896, the French physicist Becquerel discovered radioactivity by accident when he stored uranium salts next to photographic plates in his desk. And he was soon joined by many other scientists, such as Pierre and Marie Curie, as they focused their attention to the nuclei responsible for the radiation. Soon, scientists started to realize that many isotopes of an element existed, and they had to kind of divide these nuclei into two broad categories. Those that are stable and those that are unstable. So we have about 270 known nuclei that are stable, and about 4.5 times that amount we have unstable nuclei. It's the unstable ones that we're focusing our attention on because those are the ones that are radioactive. Now, we'll briefly discuss 3 types of radiation. We're going to be looking at alpha decay, beta decay, and gamma decay. As we study the different types of radioactive decay, there are a couple of key conservation laws, and these are really important actually, because it's not so much that you have to be able to classify alpha decay, beta decay, gamma decay, because we're not really have to do that in the curriculum anymore. But what you do need to know is these conservation laws. These are important because you have to be able to find the unknown mass number or atomic number in some kind of a nuclear reaction. And it really just comes down to these 2 main laws. One is the conservation of charge, Z, is conserved. So when you see the nuclear reactions, the subscripts, which are the atomic numbers, they should be the same. When you add them up on the left side and the right side of the equation, they should add up to the same amount. And then furthermore, based on the conservation of mass, the total number of nucleons, or the mass number A, must be the same. So the sum of the superscripts, the numbers from the top, they must be the same on both sides of the equations as well. So in fact, nowadays in the AP Physics B curriculum, you no longer have to identify the different names of the decay, but you do need to use these 2 conservation laws: the conservation of electric charge and the conservation of nucleon number or mass, to be able to complete these nuclear reactions. Alright, let's get into these 3 types of radiation: alpha, beta, and gamma, and let's really dive into it into a little bit more detail. So go into the next page of your notes here, and you'll see alpha decay on the next page here. So scientists had discovered, by the way, that there were alpha particles, which are positively charged, they're really helium nuclei. I'll talk about that in a second. Then there are beta particles we'll be looking at, and there are actually 2 types of beta particles. There are beta positive and beta minus. So you look down in the notes, you'll see there's a beta minus here, and then there's beta positive decay. And then lastly, we'll also have gamma decay. All right, we're going to look at alpha decay right now. All right, and there is a little bit of an error in your notes, I just noticed. This 90 right here should be a 92, and you'll see why in a moment. So alpha particles, by the way, just to kind of classify them, alpha particles are the least penetrating. They can be essentially stopped but with your hand or a piece of paper. Whereas beta particles, they can pass through the paper, but they can be stopped with, like, say, a sheet of aluminum paper. Aluminum sheet. And then gamma decay or gamma rays are the most energetic of the radiations, and they're the hardest to stop. And you need like a couple centimeters of lead or a meter of concrete to stop gamma rays. Most of the radiation is absorbed by the Earth's atmosphere. However, if you were like to be in an airplane at higher altitudes, you are actually experiencing a higher amount of this radioactivity because you're not getting as much shielding as you would get being on the surface of the Earth. Alright, let's get into alpha decay now. In alpha decay, we have what we call a parent nuclei, which is converted or transmutated into a daughter nuclei. And it also emits a particle. In this case, for alpha decay, it's an alpha particle. And an alpha particle is a helium nuclei. So if you look at a helium nuclei, it has 2 protons and 2 neutrons. So it has a +2 charge on it. That's why alpha particles are positively charged. If you think back to Rutherford's gold foil experiment, he was sending in alpha particles which had a +2 charge on them. Okay, if you look in here, you'll see a nuclear reaction. There's a sample shown here. Uranium-238 with an atomic number not 90, but it should have been 92. Okay, this parent will decay into thorium-234 and emit also a alpha particle. Now look carefully at the numbers here. Notice that the total number of nucleons, that's 238 here. That's the mass number here. 238 on the left side of this equation, and then you have 234 and you have 4. Notice that the sum of the nucleons on the right side is the same as the number of nucleons on the left side because mass must be conserved. The atomic mass number is the same. Then also look at the bottom numbers. You have 90 and 90 and 2. And I noticed this was wrong earlier because really these two numbers must add up to the number that's on the left side. Because, why? Well, charge is conserved. And if charge is conserved, the number of protons that you start off with must be the same amount of protons that you end up with on the right side. So you have to have the same amount of charge. Not necessarily you have to have the same amount of protons, because you could have electrons in the scenario as well. But you have to have the same amount of net charge, what you start off with, and what you end up with. Remember, charge cannot be created nor destroyed. So that's alpha decay. Now let's discuss beta decay. Now there are 2 types of beta decay. We have beta minus decay and you have beta positive decay. So beta particles come in 2 types. The beta minus particles are basically electrons, and the beta positive particles are what we call positrons. A positron is a positively charged electron. So it has the same mass as an electron, except it is a +1 charge instead of a -1 charge. All right, let's take a look at beta minus decay. In beta minus decay, you have this parent. For example, you have thorium, and then it decays to this daughter, protactinium. And you'll notice that it has 1 more proton now. So in beta minus decay, a neutron that was in here, because it goes 144 down to 143, a neutron is converted into a proton. And you may be like, well, how did that happen? And the force that's responsible for this neutron-proton conversion is the force we haven't talked about, but the weak nuclear force. That's what causes this transformation to occur. Not to get into much detail here, because really you don't even need to know these to be able to come up with these decays. I'm just kind of giving you a little bit of background on this. But again, look at the equation. If you look at the equation below, notice that the daughter nuclei, okay, has you have 234, and then you have this. This is, by the way, an electron, or what we call a beta minus particle. All right. But if you look at the 234 plus 0, plus this other 0 over here, and I'll talk about that particle in a second, they add up again to whatever is written on the left side. Again, mass number is conserved. And then over here you have 91, then -1, so the total charge is 90, and then you have the same charge over there. So again, the 2 conservation laws are being obeyed. The other particle here that wasn't really discovered until the 1930s, because it has very, very negligible mass and no charge, is called an antineutrino. They're very, very hard to detect. And in fact, a lot of beta decays, they don't even write this one in often in the older textbooks. Okay, now let's go on to beta plus decay. So beta plus decay is very similar. You have a proton now in the parent that is going to be converted into a neutron. It's the opposite conversion that we got in beta minus decay. So again, look at the equation here. As you can see in the equation, the daughter nuclei, so this is carbon in here, has 1 less atomic number, all right, and than what it is in the parent here, nitrogen. So it also emits, if you notice here, well, this is a positively charged electron, which is called a positron. So there's our positron. And then over here, this is a neutrino that has no mass, no charge practically. No charge, but hardly any mass. All this stuff is very interesting, but all you need to know really is just to be able to apply the conservation of mass and conservation of charge and find the appropriate, for example, atomic number or mass number, number of protons or neutrons. Okay, the last decay I want to look at is called gamma decay. Now, gamma rays are really high energy photons. Remember, photons have no mass. So if you notice over here, this is just basically light. This is energy. So a gamma ray photon is emitted from a nuclei that is in what we call an excited state. Now, to denote the excited state, we put an asterisk here. And it basically means that if you were to look at, say, the energy level diagram, here's energy here, and we have, say, ground state here, and then we have some higher energy levels here. So these are the excited states. And if you were to put the nuclei into an excited state, you would want to bring up the electron, say, to one of the higher excited states. Now, when that electron falls down to a lower state, such as the ground state, that quantum jump causes a photon to be released. And that photon is a gamma ray.